Hi everybody, today I'll show you how to do problem number 14 from the chapter 8 problem set. So it states, in the sketch at the right, a rectangular wire loop and a long straight wire lie in the same plane. The resistance in the loop is 2 ohms. A. Show that for a steady current I in the straight wire, the magnetic flux through the loop is given by flux is equal to mu I L over 2 pi ln 3. Then B. If the current in the long wire decreases uniformly from 10A to 2A in 2 seconds, find the magnitude and direction of the induced current in the loop. Let L is equal to 30 centimeters. Okay, so for part A, finding the magnetic flux, we're going to use the equation for that, and that is flux is equal to the closed loop integral of B dot dA. Okay, and if you recall from last chapter, B is equal to mu times current over 2R. So that's the magnetic field around infinitely long wire at any point R away from that wire. And this can also be written as 2Ki over R. Okay, so now plugging that in to the equation, we get the integral of 2Ki R, and then dA, so the area that we're integrating this is equal to this area of the shaded region right there. And that, since that's a rectangle, that's just going to be L times dr, base times height. Okay? And we're going to be integrating it starting from this rectangle right there all the way to this rectangle here. So what that means is we're going to be integrating it from distance L all the way to distance L plus 2L. Okay? Now, realizing that by bringing out the constants, we just get 2Ki L are all constants. Then what's left inside is this. Now we should all know how to integrate this, and you would get now this would get you and finally this you would, or at this point I'm going to change the K back into the mu over 4R, so that's or 4 pi, so that's consistent with the answer in the book. And you would get 2K would turn into mu over 2 pi I L times ln 3L over L, which just gets you ln 3. And that is the answer to part A. Okay, next for part B. Part B asks you to find the induced current in the loop. Okay, so to find that, first we're going to want to find the induced EMF through the loop. And to do that, we're going to also use this formula. E is equal to negative derivative of flux. Okay. So this, we found flux in the previous question, and we found that it was right? And I'm going to rewrite that as okay, so now in this, the way that I've rewritten it like this, I brought all the constants to one side, and then the induced current in the loop, which I separated it because it's not constant. Okay? So now when you take the derivative of that, all the constants remain the same, so you'll just get negative okay? Now you can start plugging in numbers at this point, since we know all of our givens, which is negative mu is equal to 4 pi times 10 to the negative 7 L, which is given in the problem, is 30 centimeters. So I'm going to say that's 0.3 meters. Then ln3 all over 2 pi. Then di over dt is the change in current. So we can say that's change in current over change in time. So in this problem, it tells us that so current final minus current initial is 2a minus 10a over the change in time, which is 2 seconds. And that was given to us in part B. Now plugging this all into a calculator, and you will get 2.6 2.637 times 10 to the negative 7 volts. Okay? Now, taking that answer, we can also use this formula, which we've also learned in the previous chapter, to find the induced current. So isolating I okay, the voltage that we found just earlier was 2.637 times 10 to the negative 7 volts, and the resistance that they gave us was 2 ohms. Therefore, the induced current is 0.13 microamps. Okay, lastly, to find out the direction of the current, we're going to go look at our diagram again. Okay, so looking at this diagram, we see that the current is on the long straight wire is going upwards. So using the right hand rule, the magnetic field around it is going to be directed out of the page for this on the left over here. So symbol out of the page. Okay, but in part B, it says that the current in the long wire decreases from 10 amps to 2 amps. So what that means is the magnitude of the magnetic field that it creates also decreases. So this magnetic field right here is going to be decreasing. So in that case, due to Lenz's law, the loop is going to want to induce a current that resists change. So what that means is it's going to create a magnetic field itself that goes out of the page to counter the decrease of the magnetic field of the long straight wire. And to create a magnetic field that goes out of the page, the current will have to be going counterclockwise. And you can use the right-hand rule to verify this for yourself. So therefore, for part B, the direction of the induced current in the loop is counterclockwise. Okay, and that is how you do problem number 14.